Rohit Kumar Singh. I'm the teaching assistant for this course, Wave Optics, and this is the 11th live session. And so, in the last week, we looked at polarization of light and how we can analyze polarized light using this Jones matrix formulation. So, but we didn't discuss much about how polarization happens and what are different ways of polarizing the light. So that I want to discuss today, and then we will learn about something called uh, so we looked at the phase retarder Jones matrix. So we will see that if we have if we slow down, or if we delay the phase of one of the uh, wave by pi by 2 or pi angle, then we get something called quarter wave plate and half wave plate, and that is a very useful device. will I will show you how we can get that. But okay, so uh, let's start with let's start with something basic. So one thing that we discussed last time was that if you have a polarized light, okay, so if you have a polarized light given, so polarized light, as you know, the electric field vectors are vibrating or oscillating in all the directions randomly. Okay, and when it passes through a polarizer, so a polarizer is a device which allows only a single component of this randomly oscillating electric field to pass through. So like if it has the pass axis aligned in, say, x direction, so suppose this is the x direction, this is y direction, and this is z direction, and this is the pass axis, so you get a polarized light which is parallel to the pass axis. So let's call this polarizer P1. Okay, and then so let's call this amplitude E naught. And then if you have another polarizer which is rotated like this, so its pass axis is now like this, and this pass axis is now making an angle theta with the pass axis of P1. Okay, so then, so this is P2, right? So so the component which is parallel to this pass axis of the P2 will be what, E naught cos theta, right? The amplitude, and this amplitude get passed through here, so you will get a, again a polarized light, but this, it has no amplitude E naught cos theta. And so because the amplitude here is no E naught cos theta, the intensity will be just a square of this, right? So this is called Miller's law. Okay, and if you keep rotating this second polarizer, you will see that at theta 90 degree you get nothing, so intensity is 0. So we called P1 polarizer and P2 analyzer. Okay. Okay, so yeah, this formula we didn't discuss, so this is the formula. Now it's fine. Now how does this polarizer work, that we can discuss now. So how we produce the polarized light, so production of polarized light. Okay, so one basic equipment that we can use to polarize an unpolarized light is basically called wire grid polarizer. So you take wires of copper or any conducting wire, but since copper is a very good conductor and it's very cheap, so we'll use copper. So, and you make grids of wires. So like this, you arrange copper wire parallelly between two poles. Okay, so this is a wire grid, and then you have your unpolarized light like this. Okay, and it is going like this. And let's say that this is your x-axis, this is your z-axis, and this is your y-axis. So these wires are parallel to y-axis. Okay, then what you will get here is a polarized light in x-axis. So can you tell me why? How could this happen? This is a wire grid polarizer. So this is the basic principle of polarization. Okay, can you think what could lead to this random electric field oscillations to just confine in only one direction? So to understand this, you have to look at inside a copper wire. So what is there inside a copper wire? There are free electrons, right? And you have electric fields in transverse direction. So you have, so I'm writing just the x and y components. Okay, because effectively you can resolve any electric field in any direction to x and y, right? Now the electric field in y direction, so this copper is this wire is in the y direction. Okay, so it will exert force on these electrons, right? And since these electrons are free to move inside the wire, it will perform some work given by this formula, right, in the y direction. So this distance is in y direction. But you will say force will also be in x direction, right? Why not? Because x field is there. But work done in x direction will be zero almost, because in x direction the copper wire is, very, we can assume it's a one dimensional wire. So this x, I mean, there is not much distance to travel in x direction. So this work done is almost zero. Okay. And so this electric field that is in the y direction is used up in this work. Okay. And so what remains is only the Ex. And so this electromagnetic wave is now has only the x component of electric field, so it is polarized. Okay, so this is the basic concept of polarization. It's a very simple device. Now, sorry. Wait. Yeah. Okay, so this is a very simpler picture. Do you have any question here? You understood? Okay. Now this polarizer that we are discussing here, if you, I mean, this you can buy from a market, or you might have seen anywhere. Like this polarizer is everywhere, like in the car windows you have polarizer, and in many places, like on your goggles. So this polarizer is basically made up of a thin sheet of uh, polymer, okay, some kind of material. So one such polymer is iodine. You have heard about iodine, right? So iodine has this structure that it has long chains of molecules. So long chain polymer molecules. Okay, so it's like, so in if you, the crystal structure of iodine is something like this. So it is arranged like this, parallel chains of molecules, parallel chains of atoms forming one molecule of iodine. Okay, so it is similar to a copper wire arranged parallel, and when light passes through it, it gets polarized in one direction. Okay, and there are various other such materials. There are some anisotropic crystals also, which has in different direction different arrangement of atoms. So it has some interesting characteristic that I will discuss later. But basically this is what happens. Okay, and the principle is same as this wire grid polarizer. So the electric field of the wave, light wave, interacts with these atoms. Okay, perform work in a particular direction, but in the other direction, because this chain of polymer is fixed in the crystal lattice, it won't move much. So one electric field survives, I mean one component of electric field survives, and you get a polarized light. Okay. So this is what happens when light interacts with such kind of material. You get a polarized wave. Now, there is one other interesting phenomena, which is polarization by reflection. So there are certain dielectric material, okay, so dielectric materials are basically what we call insulators, and when light falls, so when light is incident on them, and if this light is polarized in the plane of incidence, like this, okay, let's say this is the theta p of angle of incidence, then you will not get any reflected light, okay, all the light will be refracted inside the material. And the angle that it happens is called the, I mean it's the theta p, and is given by this formula, okay, it's, and this law is called Brewster's law, where n2 is this is the refractive index of this dielectric, and n1 is the refractive index of the medium through which the light wave is coming. Okay. So now instead of a polarized light, if you have a unpolarized light incident here at this angle, then you will get polarized light in the angle in the plane of incidence, okay, and reflected light will be polarized in the plane of in the plane perpendicular to the incident plane, okay. So by dot means it is coming out of the screen, okay. So this is what polarization by reflection. Now this also happens, I mean the basic principle is similar to what we discussed here. This happens, I mean this is the basic principle, but you have to for this specific material, there is this specific criteria, okay, for the dielectric materials. So I'm not going into much detail of this. I mean, I think this is not in the scope of our, this lecture. But you can study more details on this. But remember this formula, okay? So any question? Okay. So then there is another interesting phenomena which is related to polarization. It's called double refraction. Okay. So this is what I was saying, that if you have a anisotropic medium, so an anisotropic medium is basically a material which has different arrangement of atoms in different direction, okay. So if you are suppose you are a tiny human and you are standing inside that material, uh, if you look at different direction, you will see different arrangement of atoms. Okay, and that affects the light wave traveling inside the medium uh, differently in for different direction. Okay, so what I mean is, so if you have such a material like here, okay, this is an isotropic medium, and you shoot an unpolarized light on it. Okay, so you will see that there is one light ray going like this, coming out here like this, but there will be another light which is going at an angle theta. Okay, and then coming out like this. So you see that this is, I mean, this looks very weird, right? This light coming at an angle theta, and this is called extraordinary ray or E ray, and this one is the ordinary ray which is passing through normally. Okay, so from the figure itself you can see that uh, this E ray is, it does not follow the Snell's law. Okay, and one more interesting thing is this ordinary ray will be polarized in the direction of the pass axis, or okay, so let me explain what is the optic axis actually. So so along a particular direction, the velocity of this E ray and O ray given by VRO and VRE will be same. Okay, and this axis is called optic axis. Okay, and so these two rays, O ray will be polarized in the direction of optic axis, and E ray will be polarized in the direction perpendicular to the optic axis. Okay, so you get two polarized light out of one unpolarized light, and both will have different velocity in general. But if you if you are measuring the velocity in the direction of optics axis, they will be same. So let me write the formula. So so in the direction of optic axis, VRO is equal to VRE given by speed of light divided by the refractive index for the ordinary ray. Okay, along optic axis. But for an angle theta from optic axis, the velocity of the extraordinary ray is given by this formula. Okay, so along the optic axis, both ordinary and extraordinary ray, they don't have any difference. Okay, but if at an angle theta, you have this formula. and this leads to very interesting phenomena. So since now the velocity of both rays will be different, one will have a phase difference when it comes out of the this material, and then they both can interfere and give you interference, and yeah, many interesting thing can happen, right? Now if you are looking at you know angle perpendicular to the optic axis, so basically theta equal to pi by 2, uh, and you have a negative crystal. So what is a negative crystal? So basically for a negative crystal like calcite, negative crystal, refractive index for extraordinary ray is less than the refractive index for the ordinary ray. Okay, so at this angle, what is the velocity of the extraordinary ray? uh, Theta equal to pi by 2. So if you put theta equal to pi by 2 in this formula, you get C by NE, right? And this is, since NO is greater than NE, so C by NE will be greater than by C by NO, right? That means the velocity of extraordinary ray is greater than velocity of ordinary ray, okay, for a negative crystal. So this deviated light ray will travel faster than the ordinary ray inside a negative crystal, and opposite thing will happen for a positive crystal. Okay, so positive crystal is example of a positive crystal is a quartz. So here Ne is greater than No, so here velocity of extraordinary ray is smaller than the velocity of ordinary ray. So yeah, just remember this. So yeah, now as I said, since the velocity of these two will be different, so they will go through a phase difference inside the medium, right? And then you can have interference of these two uh, extraordinary and ordinary rays. So that we will look at now. So interference of these two polarized light. So do you have any question till here? Is it fine?
Sir, for a negative crystal, it is BRE, you have written C square by NE square should be there, right?
Sorry, for negative crystal?
You have written VRE is equals to C by NE.
Yeah.
It should be squared, right?
It should be?
Square. Square of
Uh,
C by NE.
oh yeah, no. This is VRE square should be here. Yeah.
Oh, okay. I'm sorry then.
Yeah. Sorry.
Okay.
Yeah. Okay. Yeah. Nice point. Anything else? Okay. Then let's move on. So now we will study the interference of the polarized light. Okay. So so let's draw a picture. So let's call this x-axis, this one y-axis. Okay, and this one is your Z axis as usual, and we have a linearly polarized light like this at an angle alpha from, or not alpha, let's call it phi, at an angle phi from y axis. Okay, so I mean this I'm drawing, why I'm drawing this, why I'm taking a linearly polarized light is because so that you know when this I mean this you can resolve into two components, right? X component, which is E naught sine phi, and y component, which is E naught cos phi, right? And now if you have a polarizer here, so if you have a polarizer here, which has the optic axis in this direction, in the x direction, so then the x component will be your O ray, ordinary ray, and the y component will be your extraordinary ray, right? And the velocity will be given by here c by no, and here the velocity is given by, so if you put pi by 2 in this formula, you will get c by ne. And if this is a a negative crystal like calcite, for which Ne is less than No, then extraordinary ray velocity will be greater than the velocity of ordinary ray. Okay, so that means the extraordinary ray is the y component, so we call the y axis as fast axis denoted by f, and x axis as the slow axis denoted by s. Okay, so these are some nomenclatures. Okay, now to study the interference, first let's write the x and y components of the electric field. So you have E naught sine phi, the amplitude, and then you have the the wave component given by this formula. Okay, so here instead of k, we have written n naught k, which is the refractive index gets multiplied, right? So this is your ordinary one, and the extraordinary one, which is in the y direction, is your E naught cos phi and cos of, here Ne will be there, right? This is your extraordinary one. Okay, now suppose this this polarizer has a thickness d. Okay, so it is it has a thickness of, oops, it's a very wrong picture. Yeah, I mean I don't know what I'm making. Okay, so it has a thickness of d in the z direction. This is z direction. Okay, so then you can take 2 points, so at z equal to 0 and z equal to d, right? So at z equal to 0, uh, what will be your Ex and Ey? So at your Ex will be simply E naught sine phi cos omega t, right? Ey will be E naught cos phi cos omega t, and at z equal to d you will have E naught sine phi cos n naught kd minus omega t, and y component E naught cos phi cos of n e k d minus omega by t, right? And now you see, from going from 0 to d, there has been a shift of phase, right? But these two shift is different. I mean the theta 1, the phase shift here is NOKD, and the theta 2, the phase shift here is NEKD. And because NO is greater than NE, the relative phase difference, which is given by theta O minus theta E, so let's call it theta O and let's call it theta E, which is KD NO minus NE, or you can write it in terms of frequency and speed of light, which is WC NO minus NED. So this is the phase difference that is introduced by this polarizer, okay, between the extraordinary and ordinary ray. So they can now interfere, right? And we have studied in the last lecture what happens when two polarized light interferes, right? So if there is polarized light in one direction, in x direction, and another one is in y direction, and if they interfere, they if you superpose them, you will get a right circularly polarized light, and you can get elliptically polarized light, and so on. We discussed that, right? Do you remember? So that those things can happen here. So for example, if there is a shift of pi by 2 between them, okay, this polarizer is called a quarter wave plate, okay. So why quarter wave plate? Because pi by 2 corresponds to 1 by 4th of the wavelength, right? And so in this case, now your x and y component is basically, and let's take this phi to be 45 degrees, okay, for now. So your x and y will be, so Ex will be E naught by root 2 cos 45 is 1 by root 2 sine omega t, and Ey will be E naught by root 2 cos omega t. So I shifted one of them by pi by 2, so that's why cos became sine here, okay. Taking the relative difference. Is it fine? Now, if these two are superimposed, what do you get? Remember from last lecture, you get the linearly circularly polarized light. Sorry, not linear, left circularly polarized light, okay. You remember? So a quarter wave plate, when acts on a linearly polarized light, it converts it into a left circularly polarized light. And you can also have a phase difference of pi, which is called half wave plate, because it is half of the wavelength. Pi corresponds to half of the wavelength, and in this case your Ex will be, so cos omega t plus pi is just minus E naught by root 2 cos omega t, and here it is E naught by root 2 cos omega t. So what this will correspond? So both have this cos omega t component, right? But their amplitude is in different, with different sign. So you must remember this is a case of linearly polarized light, right? But with an angle which is greater than 90 degree, right? You remember the phi was what? Tan inverse plus minus A by B, right? So this will for this will lead to 135 degree if you put these two as A and B, okay? And so on. You can have, so if now at this angle your amplitude is different, you will get a elliptically polarized light and so on. But yeah, basically this is what happens, okay? So if you have a linearly polarized light, you apply a quarter wave plate, you get a circularly or elliptically polarized light. And if you have a linearly polarized light and you apply a half wave plate, you will get again a linearly polarized light, but it will be rotated by an angle, 90 degree angle, okay? So earlier it was at 45 degree, but now it is at 135 degree from the y axis due to the half wave plate. Is it fine? So last time we did this analysis, I mean we had this phase retarder matrix, right? If you remember. And so for quarter wave plate, this phi is just pi by 2, right? But this is for when you have a negative crystal. So till now we have discussed for negative crystal where NO is greater than NE, okay? So as you can see here, and if you do the same derivation with a positive crystal, you will see that the phi comes out to be negative, okay, minus of pi by 2. This is for positive crystal. And the and we know that phi is given by 2 pi by n o minus n e d, okay? So here the theta now it's given by phi basically here. So using the notation of the Jones matrix, but it is the same thing, okay? Don't get confused. And so for quarter wave plate, when you have the so here we write Fy because our y-axis is the fast axis, right? Here I denoted y-axis as the fast axis, so I'm writing Fy, and if you put pi by 2 here, you will get I 0 0 1. So this is the Jones matrix for a quarter wave plate, and similarly there you can write a Jones matrix when you have the slow axis in the y direction, so you will get minus I, okay. So this is when fast axis along y direction, and this is slow axis along y direction. So I mean it just means that fast axis along y direction means the extraordinary wave has extraordinary ray which is in the y direction has larger velocity than the ordinary ray, and opposite to then opposite thing for this other one. And similarly for half wave plate, the Jones matrix, you can put phi equal to pi, you will get minus 1 and 0 0 1, and this is true for both theta equal to pi and minus pi, okay. So both for both negative and positive crystal you have the same quarter wave plate, okay. And also one thing you can see, like if you apply the quarter wave plate 2 times, so pi by 2, you basically get a pi phase difference, right? So you get a half wave plate, and that should also be true in this matrix formulation. So what I am saying is this should be equal to this and again this. So you can verify, multiply these two matrices, you should get this matrix, for consistency. Okay. So this is the Jones matrix formulation for quarter wave plate and half wave plate, and we will use this for solving our problems, okay. Is it okay? Any question? Okay. So then let's go to some problems. So there is one true false. So choose the correct statement for anisotropic crystals. So optical properties are same in all direction, optical properties are different along different direction, optical properties are unaffected by the crystal rotation orientation, the arrangement of atoms is same in all directions. So which one is the true option? Can you see?
Second.
Second, yeah. Okay, that was easy. Then again an easy one, the polarizing angle for air water interface is so what is the formula?
N2 by N1.
N2 by N1, right? 1.33 by 1. So you can calculate. Okay, again an easy one. Okay. Now here is the one problem on this Miller's law. So an unpolarized beam with an intensity of so this is given initial intensity, and it is passing through two polarizing filters. Okay, the pass axis of the first filter is rotated at an angle 18 degree, okay, to the vertical, and the pass axis of the second filter is rotated an angle 43 degree to the vertical. So it's asking what is the intensity of the transmitted beam. So okay, so let's call theta 1 18 degree, which is the pass axis of the first filter, and theta 2 is 43 degree. Okay, uh, now when the light okay, let me draw. So here is the first polarizer, here is the second polarizer. So what I told you, so here is the unpolarized light. When it passes this first polarizer, it will be polarized at an angle 18 degree to the vertical, right? So, and but what will be its intensity? So intensity is given by this
Not
formula.
cos square routine.
So you're saying the intensity will be cos square 18 degree, right? That's wrong. This Miller's law is valid for polarized light, okay? It's not valid for an unpolarized light. This is not correct. So this first polarizer, okay, which is polarizing then unpolarized light into one direction, it reduces the intensity by half. Whatever intensity you have in the unpolarized light, it reduces it to half. Why reduce it to half? Can you think about it? Because see, uh, you can resolve all this unpolarized electric field into two direction. One along the axis of the uh, pass axis of this polarizer, and one perpendicular to the axis of this polarizer. Okay, and so you get half after the first polarization, because it cuts off the perpendicular one, it only allows the parallel one to pass through. Now when you have the polarized beam here, then this Miller's law applies, okay, and then uh, the final intensity will be I naught by 2 cos square the angle difference between these two, okay, which is 25 degrees, okay, and this will give you the intensity of the final transmitted beam. It will be around 84. So D option. So remember this, don't blindly use the equation, okay. The first polarizer will just reduce the intensity by half, just remember this. Okay, now let's go to the second one, second one on the same concept. So there are two crossed polarizer crossed polarides placed in the path of a unpolarized beam of intensity I naught. So again you have unpolarized light of intensity I naught, okay, and there are two polarides which are put like this, and then the third polaroid is placed between the two of them. Okay. Assuming the pass axis of the third polaroid is 45 degree to the pass axis of the either of the polarides. Okay. Okay, so what does it mean? So two crossed polarides placed in the path of an unpolarized. So does it mean that one is like this, other one is kept like this, and this third one uh, is at a 45 degree. So this is the pass axis and this is the, and this angle is 45 degrees. Okay, so this is the problem. Now here I naught, when passing through this polarizer, it will become I naught by 2, right? And then this I naught by 2, so going here will be I naught by 2 cos square 45 degrees, right? And then when this crosses the third polaroid, so let's call it I2. Okay, you will have here, let's call it I3. I3 will be, again, because this is rotated at an 45 degree angle to this, you will have I2 cos square 45 again. Okay, so finally you will have I naught by 2 and cos to the power 4 45 degree. Okay, so finally finally you will have I naught by 8, right? Because cos 45 is 1 by root 2, so you get 4 times, you get 2, you get 4, you get 4, and then into 2 is 8. Okay, so this is the correct option. So this way you have to deal with these problems. Okay, okay, now moving on, next one. So consider a quarter wave plate whose slow axis is along x-axis. Using Jones matrix, the output state of polarization when the incident beam is linearly polarized with its electric field making an angle 30 degree with the y-axis. Okay, so we have to use the Jones matrix, and for a quarter wave plate whose slow axis is along x-axis, that means fast axis is along y-axis. So that's what we have derived, right? Which is given by this formula. This is our Jones matrix. Sorry, I001, right? And the incident beam, incident beam is the one where this matrix will be applied. So incident beam is linearly polarized. So we know the the matrix of the linearly polarized beam at an angle alpha, right? Cos alpha by sin alpha, you remember? And this alpha is basically angle with x-axis, not with y-axis. So remember that. So here the 30 degrees given with respect to y axis, so this alpha will be here 60 degrees, right? So cos 60 is 1 by 2 and sin 60 is root 3 by 2. So this is our linearly polarized light, and we have to find the output when this applies to this. So we just do this matrix multiplication, and it is straightforward. So you will get I 3 by 2. Okay, so what does this represent? Is it a linearly polarized light? Is it a left circularly or right circularly, or an elliptically polarized light? What do you think? Any idea? So this is basically, here you have, this is the x component is given like this, y component is given like this. So first of all, you see the amplitude is different, right? So it cannot be circularly polarized. It should be elliptically polarized, because A is not equal to B, if you remember the last lecture that we discussed. And this I means that the amplitude is shifted by e to the power I pi by 2. So there is a pi by 2 shift in the x component. So it is right elliptically polarized. Okay. So first thing you have to notice is the magnitude. If the magnitude is different, then already it is elliptically polarized, and then if it is right or left, that you need to understand by the angle, like if Ex is leading or Ey is leading. Okay. So we discussed this, if you remember, like if you have Ex is equal to A cos omega t, Ey is equal to A sin omega t, if theta is equal to pi by 2, and we put B equal to A. So if this was B, then we analyzed on different time frames, like what happened at t equal to 0, what happened at t equal to pi by 2 omega, and so on. And from here we concluded that this case will give you an right circularly polarized light. Do you remember? So similar thing you can check for this. Okay. So you will see that you will get a elliptic polarized light like this. Okay. So moving on. Now again, instead of quarter wave plate, you have now the half wave plate, and its slow axis is along x axis. Okay, fine. So using Jones matrix, we have to find the output of the polarization when incident beam is left circularly polarized. So now we have left circularly polarized beam. So you know that the left circularly polarized beam is given by uh, which matrix? 1 minus I, right? And the normalization. This we discussed last time. And for, sorry, the half wave, the Jones matrix for half wave plate is given by I wrote it earlier like this. Okay, so you have to just operate it on this. So minus 1 0 0 1 on 1 minus I, okay, you will get minus 1 by minus I, right? Is it okay? Wait, left circularly is yeah, it's fine. Yeah. This is a long axis. Okay, so now you see what you have. You have this, and this you must remember, right? This is a Jones matrix for right circularly polarized light, right? I mean this amplitude is constant, but both have no positive sign because negative sign is taken common. So what half wave plate does is it converts a left circularly polarized light into a right circularly polarized light. Okay, so C is the correct option. So all these things you can do it using this electric field analysis also. Like you write an electric field for left circularly and right circularly polarized light, and you will see that by introducing a phi a phase shift of pi, the left circularly polarized light will become right circularly polarized light. But with the Jones matrix it is very straightforward to see, right? You have to just do a simple matrix multiplication. Yeah. So is it clear, or do you have any confusion? Should I move on? Okay. Okay, so okay, another problem. So consider a quarter wave plate followed by a half wave plate, and the slow axis is along x-axis. The Jones matrix for the combination. Okay, so whenever you get this kind of problem, this means that okay, there is a quarter wave plate, okay, and then you have a half wave plate, right? So what will be this combination become? So you have the matrix for quarter wave plate and you have the matrix for half wave plate. Just multiply these two, okay? So you have I0 0 1 minus 1 0 0 1. So you know the matrix multiplication. Let me do it. So this is minus I. Here you will get 0. Here you will get 0 and then here you will get 1. Okay. So this becomes again a quarter wave plate, but now the slow axis is along y direction. Okay. So this corresponds to this quarter wave plate with slow axis along y direction. Remember, I discussed it here. Okay. So this is also simple. Okay, another one. So now a right circular polarizer acts on a wave linearly polarized in x direction. What is the output Jones vector? So this one is tricky, and this one requires some knowledge of, not much, but some knowledge of linear algebra, or if you studied quantum mechanics, then it's very easy to solve. But I will explain how you can solve this. So it is saying a right circular polarizer acts on a wave linearly polarized in x direction. So you know that linearly polarized wave in x direction, it is just 1 0, right? This we know, right? Now but how to represent okay, and also we know the right circularly polarized the right circularly polarized vector, which is 1 by root 2 1i.
We can write it the x get x as 1 by root 2 RCP plus LCP. Like that?
No, no.
No.
That will give you
Okay.
this. That will give you this, right? But you don't want this. What you want is the Jones matrix for right circularly polarizer. Like, which Jones matrix is your like when it acts on a wave, okay, make the wave a right circular polarized light. You want that matrix, and then that matrix you need to apply on this to get your answer. Okay.
Okay.
So now to solve, no here comes the power of Jones matrix, because you know don't even if you don't know anything about optics, okay, and you if someone is from mathematics department, and just you give them this information, they will solve this problem in fraction of seconds, because they know linear algebra. Okay, what I mean is, see, there is something called okay, there is something called projection operator. Okay, so what I mean is yeah, so these vectors, Okay. uh, I don't know. Do you guys know about eigenfunctions and eigen values? Have you heard about it?
Yeah, only heard about it,
Okay,
don't know
okay.
about like.
Okay, no problem. Okay, let me try to explain what it means. So, okay, so uh, like when I was discussing this Jones matrix, I told you any vector that you take. So, suppose you have a vector A, you can resolve it in terms of uh, unit vectors I and j, right? These I and j's are called your unit vectors, or they are called bases in terms of linear algebra. Okay, and so any vector can be written in terms of I and j, and in our case we can write any state of polarization in terms of x and y. So x and y are our bases here, but these are not special, right? You can take any basis you want. For example, I will say that okay, I will take a different set of bases in this direction and in this direction. So I will call it I prime and j prime. I will use this basis. It is perfectly valid. It is a unit vector. It is valid. Similarly, you can have RCP. Sorry. Yeah, you can have RCP and LCP as your basis. Okay, it is a vector, so you can use them as a basis. And for a basis, for example, here I dot I, you know that it is 1, right? Because they are unit vector, when you multiply them you get 1. Similarly, when you multiply this, you should get 1, which is what you get, right? 0 1. Sorry. So okay, one more thing. So this is a Ket notation, and if you invert this bracket, you get I mean this is basically a transpose. Okay, so this is 1 0, so it is now 1 by 2 matrix. So this is how you multiply two vectors in linear algebra. So this is now 1 0 multiplied to 1 0. So 1 cross 2 matrix multiplied to 2 cross 1 matrix. So this is the you will get 1. Okay, it's a scalar. And similarly, RCP should also be equal to 1. You can check it. All these vectors, when you multiply with themselves, will be equal to 1. Okay, for example, so let's do it. So you have two factors, and then you have 1 I multiplied with multiplied with 1 I. So you have 1 by 2 here, and here you will have wait 1 I okay. So 1 plus I square, right? Oh, sorry, no, when you take the conjugate you get negative sign here, so I becomes minus I. So 1 plus 1, so you get 1. Okay, complex conjugate, complex conjugate of I is minus I. Okay, so when you take a conjugate matrix of this you get a you have to use minus I instead of I. So these are, these are stuff from linear algebra, or when you study quantum mechanics, these things will be much more clear. Okay, but what I wanted to do here is, I don't want to teach you linear algebra, but let me do what I wanted to do, otherwise you will be confused. So okay, so there is something called projection operator. Okay, so projection operator, and this projection operator is this is for any vector. So for example, for x, the projection operator is this quantity. Okay, and when you apply a projection operator, so when you will apply this projection operator, so let's call it px on x, you should get the X matrix. Okay, which is evident here, right? Because if you apply this on this, so this is 1, so you get this. Okay, so this is a single line. Similarly, for the projection operator of right circularly polarized light, you should have RCP, so that when this projection operator gets applied on a right circularly polarized light, you get a right circularly polarized light. Okay, because this is just RCP, and this is equal to 1, so you are left with RCP. Okay, so what I am saying is, so the matrix which is which gives you right circularly polarized light is basically given by this projection operator. Okay, and this you can calculate, because RCP is this, and the conjugate part you can write like this, 1 minus I, and so now you have to just multiply these two matrices. So 1 by under root 2, 1 by under root 2 is 1 by 2, and you have 1 by I, and you have 1 minus I. Now this is not a scalar, this is now another matrix. This will be a 2 by 2 cross 2 matrix. Okay, so there is a difference between when you have this and this is a scalar, but if you have this and this is a matrix. Okay, so just keep that in mind. Okay, so this will give you the matrix which, when acts on any state of polarization, it gives out the right circularly polarized light. Okay, so you can calculate this, you can do this matrix multiplication. So you will get 1 here, minus I here, and I minus I square is minus 1, so 1 here. Okay, so this is your matrix for right circular polarization. And now when you apply this right circular polarization matrix on your wave which is linearly polarized in x-axis. So that means you just do this matrix multiplication, 1 by 2 is 1 and I. So what do you get? You get basically this, which is a circular right circularly polarized light, right? Now, okay, so if you got confused, let me again explain something with, you know, vectors. So what I'm saying is, when you have these two bases, okay, in our case this is this right circularly polarized light. The projection operator is basically, you know, the projection operator projects any vector in the direction of you know, so suppose you have a projection operator for x-axis given by px, then it should give out the component of this vector in direction of x direction, okay. So when projection operator applies on any vector a, you should get ax, okay. So this is what we have done in the above formulation. So we have this polarization projection vector which is given by this, and this you can see that here it can be you can use the projection vector as so you know, you can represent I as 1 0, yeah, like a dot product. So you can it is not a, so then your projection operator here will be 1 0 and 0 1, okay. And this when applied on any vector, it gives you the x component, okay. So if this projection operator applies on any state of polarization, it basically gives out the you know, the this quantity basically, whatever the component is there in this direction. I know it's it's a little confusing for you, but yeah, just I want you to remember one thing. If you get a problem like this, so whenever you get a problem like you don't know the polarizer, I mean you don't know what is the matrix for a polarizer, but you know the vector corresponding to that state of polarization. So then you can construct the matrix using this formula, okay, which is just the matrix multiplication like this. So this will be the Jones matrix for your state of polarization. So this you can construct for any state. So suppose someone asks what will be the Jones matrix for you know, this state of polarization. So it will be simply what, this thing, which is 1 0 and 1 0, which is when you multiply this, it will be 1, it will be 0 here, and then it will be 0 here and again 0. So this is the Jones matrix for polarization in x direction. Similarly, you can calculate polarization, Jones matrix for polarization in y direction like this. right? Similarly, you can calculate the Jones matrix for left circularly polarized light, which will be uh, LCP, LCP. You know the matrix of, you know, vector for, I mean matrix of this LCP. Tx would be 1. Yeah, it's 1. It's 1 here, right? So do you understand what I mean by the projection matrix?
Yes, sir.
Okay.
A little bit.
Yeah. So if you think it in terms of basically, you know, vectors, it will be clear. So I mean, what does this projection matrix does is it basically gives you the component of the vector in the direction of, you know, whatever state of polarization you are looking. So, but yeah, if you study further quantum mechanics or linear algebra, it will be more clear. It's very interesting. Yeah. But for now, you can remember this formulation, and you can solve the problems very easily. Okay, so yeah, this was the last problem. So thank you. Any question or doubt? So one thing, we will have our extra. So we will have our extra session on Tuesday. Okay, 6 p.m. Is that fine, or do you want to change the time?
Upcoming Tuesday.
Yeah, upcoming Tuesday, 7th.
No, 6 to 8 is not fine because 7 to 8, my place is very much noisy.
No, 6 to 7 we will have only 1 hour. That will be enough.
Okay.
So 6 to
Do
7.
like we don't have more of these official lectures.
No, we have one more next Saturday, but I want to have one extra session of 1 hour.
Yeah,
So
okay.
okay, so Tuesday 6 to 7 we will discuss the Febvre Perot, and also the question that you asked about, you know, the formula of mirror formula, why we get the negative sign. So I will also discuss that. Okay. So
Yeah.
okay. Okay, so then if there is no more question for today's stuff, we will close the meeting and see you on Tuesday. Okay.